Let's prove using Lagrange mean value theorem that e to the power x lie between 1 plus x and 1 plus x times e to the power x for every real number x greater than 0. Let's state Lagrange mean value theorem. Lagrange mean value theorem states that if a function f is continuous on the closed interval a comma b and differentiable in the open interval a comma b, then there exists a real number c in the open interval a comma b such that f dash of c equal to f of b minus f of a divided by b minus a. We want to use this theorem, or we want to apply this theorem, so we should decide about what should be our function f, what should be the interval a comma b. To do so, let's recall what we need to prove, or let's write what we need to prove. To prove e to the power x is greater than 1 plus x. Once again, e to the power x is greater than 1 plus x and less than 1 plus x times e to the power x. Somehow we want to use the fact that f dash c equal to f of b minus f of a divided by b minus a. Maybe we can choose fx equal to e to the power x. Then what about b and a? To decide so, observe that if I subtract 1 from this inequality, then this inequality can be written as e to the power x as it is less than as it is. Let's write whatever as it is, 1 plus e to the power x greater than 1 plus x. And we subtract 1 throughout. So minus 1, minus 1, minus 1. Well, we can cancel 1 and 1 out. We can cancel 1 and 1 out. And so we get e to the power x minus 1 greater than x. Once again, e to the power x minus 1 greater than x less than x times e to the power x. Observe that these two inequalities are equivalent, because if I add 1 to this inequality, then we get this one, and if I subtract 1 from this one, then I get this one. Now you see, we get something like f of b minus f of a. So we define fx equal to e to the power x on the interval 0 comma b. Let's do it that way. F of 0 is e to the power 0, which is 1. F of b is e to the power b. We can replace b by x. Then, of course, b is greater than 0. Then f is continuous. F is continuous on closed interval 0 comma b. That's obvious. Exponential function is continuous throughout R, so it should be continuous in this interval as well. Comma f is differentiable on the open interval 0 comma b by Lagrange mean value theorem. Once again, by Lagrange mean value theorem, comma, there exists a constant c such that f dash of c equal to f of b, that's e to the power b minus f of a, that is e to the power a, e to the power 0, divided by b minus 0. Okay. Now what about f dash of c? Fx equal to e to the power x. Then f dash x is also e to the power x. The function quite easy to differentiate, right? Derivative is that function as well. So f dash of c is e to the power c equal to e to the power b minus e to the power 0 is 1 divided by b. And that constant c lie in the open interval 0 comma b, that is c is greater than 0 less than b. So if c is greater than 0 less than b, that implies e to the power c is greater than e to the power 0 less than e to the power b. So if e to the power c lie between 1 and e to the power b, we conclude that e to the power b minus 1 by b must lie between 1 and e to the power b. Now b is an arbitrary positive real number, b is just greater than 0, so we replace b by x. Since b is a positive real number, comma, 1 is less than e to the power x minus 1 by x, which is less than e to the power x. We can multiply by x throughout, x is a positive real number, and add 1 to obtain x plus 1 is less than e to the power x. X plus 1 is less than e to the power x, and that is less than e to the power x times x plus 1. Are we done? Yes, for every positive real number x.